Recording. There we go. All right. In a voltaic cell, if we increase the concentration of the ion in the cathode half cell, so we have, if we have the cathode half cell, that's going to be the reduction. So our metal ion will be M2 plus 2 electrons goes to M. So if we increase the concentration of the ion, that means we are increasing the concentration of product or reactant? Reactant. And if we increase the concentration of the reactant, that means that Q is going to become smaller. And if it gets smaller, is that getting closer to equilibrium or further? That's getting further from equilibrium. And if it is further from equilibrium, then the cell potential will get, remember, at equilibrium, E naught cell is equal to 0. So if you're getting further from equilibrium, E naught cell needs to be getting larger. B is just the opposite of A. Now, if we go to our anode half reaction, that's going to be an oxidation. So that's going to be the metal becoming metal 2 plus 2 electrons. So if we increase the concentration of M2 plus, that means we have increased the concentration of reactant or product. That one would be? It's on the right-hand side. It's the product. Okay, so we've increased concentration of product, and that means that Q is going to become bigger. And if Q becomes bigger, are we getting closer to equilibrium or further from equilibrium? Closer to equilibrium. How do we know that? Because KEQ for these is large for an electrochemical cell, for a galvanic cell. And if we're getting closer to equilibrium, then E naught cell is getting smaller because we're getting closer to 0 volts at equilibrium. Is good? Cool. Anybody else got questions? Okay. If nobody has questions, we will carry on with electrolysis. And last day we got to here. Did we get to here? Where did we get to? We got to 116? Okay, and we finished 116, is that correct?
Yeah.
Yes, okay. So, page 117, we're now going to take a look at this, and we're going to say if we have a solution containing lithium ions and I- ions undergoing electrolysis using inert electrodes, so we don't have to worry about the electrodes doing anything. They're not going to get reduced or oxidized or anything. Let's see who will be preferentially oxidized. So you are going to want, if whoever's going to be preferentially oxidized will have the, what type of E naught ox? Will it have the highest E naught ox or the lowest? Highest oxidation potential or lowest oxidation potential? Highest. So basically, we're going to list all our species, and it is really difficult, I find, for most students to kind of just list the species at the start of this unit. So I would really recommend just drawing a little beaker and saying, okay, I've got a beaker and I've got my electrodes, and it tells me they're inert, so I'm going to make them out of carbon. And I'm going to have a battery here. How do we draw a cell or a battery? We draw one line, one long line, and one short line. And the long line is the positive, and the short line is the negative. So which direction are electrons flowing? Are they flowing from left to right or from right to left? They're flowing from left to right because they're attracted to the positive terminal and they are repelled from the negative terminal of the battery. And we have a solution. And if we have a solution, that tells us that not only do we have lithium and iodine, but we also have water. So we're going to draw all of those things in our beaker. We have lithium plus, we have H2O, and we have I minus. And then we say, list your species, Li plus, I minus, and H2O. And first of all, decide, can they be oxidized? If they can, what is their oxidation potential? Lithium, positive, cannot be oxidized. Because what would happen if lithium plus were to lose an electron? It would become lithium 2 plus. Have you ever seen such a thing? Would it be easy to remove that electron that is now in a shell that is now closer to the nucleus? No, because you removed one from the outer shell, now you've got that inner shell. So yeah, there's no such thing as Li2 plus. So we can just omit that entirely so we don't have to worry about that. Now we have I minus, and it can be oxidized if it goes this way. This is what the table says. Okay, this is our reduction potential from the table. And that means that the oxidation potential is going to be the reverse of that. So that is negative 0.54 volts. So far, so good? Okay. Now water, if it says a solution, you have to remember water. And most often, the water used is going to be in the gray highlighted section. I guess it's low lighted rather than highlighted, but whatever. And you need to look for the oxidation of water. So you need water to be on the right-hand side, right? Because it's going to be going this way. It's going to be to lose electrons. And this, of course, is the reduction potential, but we're looking at how good is it at being oxidized, so we want the oxidation potential. So we make that the opposite sign, so that is negative 0.82 volts. So out of these two choices, what is the preferred reaction, preferred half reaction? The iodide, yes? So that's our preferred oxidation, half reaction. Okay, take care. Sometimes you'll be told something is an acidic or basic solution or neither. And if you have acidic or basic solution, the potential for the reduction of water will change. So the reduction potential changes if the reaction takes place in basic solution. Why is that? Because if you look at here's water, and if you look at the reduction of water, if you look at the reduction of the water, hydroxide is part of that half reaction, yes? So if you were to increase the concentration of hydroxide, what would happen to that cell potential? You've increased product. And if you increase product, then Q is going to be bigger, so you're going to be closer to equilibrium, which means the voltage is going to get smaller, more negative. Okay? So what will happen is if you have the reduction of water and it's in basic solution, you have to drop down to the other water, the other reduction of water, which has a less favorable voltage. So what's the difference? This one up here says 2OH minus 10 to the negative 7 molar. So you are going to use that for neutral or acidic situations. Why is it also okay for acidic situations? I guess because it just means that the concentration is really low, and if it's even lower, then it's not going to make that much difference, I guess. It never made me feel really happy that there's not like one where it's smaller, but I don't know. So for acidic or neutral, use that one. Use this one for basic. Yes? Okay. Similarly, for the oxidation of water, so here's water, here's our oxidation, and we would normally use the one that's low lighted in gray. However, if we have acidic solution, the oxidation potential changes because hydrogen is part of the oxidation water half reaction. So normally, without extra hydrogen, we have 2H plus 10 to the negative 7 molar, which is the concentration, which is a neutral concentration of hydrogen, yes? That rings bells? 10 to the negative 7 molar, pH 7, yeah. Okay, and that is negative 0.82 volts because, of course, we're going with our oxidation potential. But if we have more hydrogen, is hydrogen a reactant or a product in this situation? It is a reactant, which means we're increasing concentration of reactant, which means that the Q is getting, is Q getting smaller? Oh, that's not making sense to me anymore. Oh no, it's a product. Sorry, H is a product. H isn't a reactant. That's why it's not making sense. H is a product because we're going to the left. I got to point that way because on my screen it's this way, but for you guys it's that way. We're going to the left. Okay, so H is a product. So that would make our Q value larger, which means that we are closer to equilibrium, which means that we're going to be more negative. Yes? Okay. I don't know that that's the best explanation. You actually are never going to have to explain that. You're never going to have to explain why this voltage is smaller. I don't even think this could possibly show up on AP. This is only in the regular chem. Okay, because do you get this nice big table in AP? No, you only get the reaction potentials that you need. They will give you like this one and that one. So you're not going to have to make a choice between the two waters, but you might in regular chem. Okay, so all you need to know for regular chem is if it is acidic, you're going to use this one. And if it is neutral or basic, you're going to need to use that one. Yes? Okay. And you don't need to explain it. A couple of useful rules of thumb that can just make things quick for you. So remember, you're making a choice in any of these situations. You're saying, I have several things, like maybe I have lithium and iodine and water. Which one is going to get oxidized? Which one is going to get reduced, et cetera, et cetera. Well, one of the things that's going to make your life a little bit easier is that group 1 and 2 metals will never be reduced. Okay, metal ions. So that would be like Li plus, Na plus, K plus, etc. It's because they're really weak. Yeah. So if we look at them, they are all down here. Yes? They are all weaker than water. Yes? So you don't even have to think about them. You can just be like, it's sodium. It won't become reduced. We can reduce sodium, but what would we have to do with our salt instead of dissolving it? We would have to melt it so there's no water around. If you just have sodium and no water, you can reduce the sodium. Yeah? Okay, and that's because we have water having the higher E naught reduction. All of these guys down here are lower E naught of reduction. We good with that? Okay, very cool. So group 1 and group 2, you can just kind of ignore them. They're all down at the bottom of the table. Secondly, polyatomic ions will not get oxidized. Now, if you forget any of these things, you can just use your table, right? You can be like, can it happen? And do the comparison. But all your polyatomic ions, when you see them on the left, they're all up near the top. Yes? So first of all, most of them are on the left, so most polyatomic ions get reduced. And that's because they usually have oxygens on them, so you're busy taking oxygens off of them. And if you take oxygens off, you are getting reduced. So polyatomic ions usually don't get oxidized. Let's see if there are any over on the right-hand side. There is really only sulfate, yes, And if you look at sulfate, which is the only polyatomic ion that could get oxidized, water is going to, oh, I copied this and it's wrong. Okay, we need to fix this. Fix. This should say negative 0.82 volts. So water would be preferentially oxidized. Yeah? You good? Okay. So mostly they don't get oxidized. Sulfate could get oxidized, but if water's around, it won't. Which is one of the reasons why it's a really good ion to use. Okay, so our type 1 cell was that first type of cell that we looked at where we had our electrolyte, which is usually our salt. And in that case, it is molten, in other words, melted liquid. This is the simplest type. You don't have to really do many comparisons because your positive ion is going to get reduced, your negative ion is going to get oxidized, and that's all there is to it. So if you see yourself with a type 1 cell, you're going to be like, so nice, so easy. Yes? While we're here, could you please label the cathode and the anode on this cell? Usually the easiest way to do it is to say this is positive, this is negative, therefore my electrons go this way. And if they're going that way, this must be the anode because it's losing electrons. And this must be the cathode because it's gaining electrons. So that's the way I find it the fastest or the easiest to figure out who's the anode and who's the cathode. Yes?
I know this is like totally unrelated.
Uh-huh.
What's the difference between non-spontaneous and non-reactive?
Non-spontaneous, not reacting means if you don't plug it in, it won't go. So the reason the reactions in this cell will occur is because we are powering it with a battery.
So it would be...
It is a non-spontaneous process, but we can make it go if we plug it in.
So basically non-reactive is the same as non-spontaneous.
Yeah.
So you can use the cell, you can make this non-spontaneous reaction with the spontaneous reaction.
Yeah, so you can either have a battery or a cell or a DC power supply that you just plug into your wall, okay? Yeah. All right, so here we have some molten potassium bromide that is being electrolyzed, and you guys are going to label the positive and negative terminals of the battery, the direction of electron flow, anode and cathode. We're going to cross out for, the direction of ion flow and the material that the electrodes are made of. And then once you've done that, you're going to calculate E naught of the cell. And if anyone sees a large silver contigo bug around somewhere, be like, there it is. I think I might have left it in the staff room. But it makes me sad because it's got my tea in it. But it's probably in the staff room. Because I had to carry a whole stack of things back, so I imagine I left that there by mistake.
No, but this one. Because this is gonna be more positive than just best. No, it's just the other way.
Gotcha.
No.
Ooh, you know what else you could do? You could write the half reaction at each electrode. Yeah, VII. Now, if you're checking your answers and you got something different than me, make sure you understand why. So let me know if you're like, hey, how did you know that the one on the left was the anode? Or how did you know where the potassium went? Or whatever. Yes. How did I know that the electrodes are made of carbon? That's a good question. Because we're dealing here with type 1 cells, I know that they have to be inert. Okay. And because I've got a molten salt here, I don't want to use platinum or gold because they would melt at the same temperature that the salt melts. Does that make sense? All type 1 cells, going to use graphite. Yeah? And so when I say carbon, I really mean graphite, but I can't fit the word graphite on there, so good question. Any other questions? Yes. How did I know that K is going to go to the right? Because it is a cation, and cations go to the cathode. Yeah. I mean, that's the easy way of looking at it. The other way to look at it is to say my electrons are going here. Who's going to come take them? The positive ion. Yeah? Yeah. The electrons are leaving here. Where did those electrons come from? They came from the negative on the BR. Yeah? Any other questions? Okay, shall we try the next one? Ooh, we have to do what is the minimum voltage that must be supplied by a battery or a DC power supply in order to make the cell run? How do we answer that? Yes. Yep. Anything greater than 4.02 volts. I don't know. I don't know. Let's see what Hebden has to say about electrolysis. La, 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 la. La, 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 la. I don't know. Just don't worry about it. Okay? Let's just, nah. Okay. Draw a fully labeled diagram of an electrolytic cell that has molten magnesium chloride as the electrolyte. That's going to include your movement of your electrons and the movement of the ions. I have to be honest, I usually use DC rather than a battery because I know that I can get exactly the correct voltage. You know what I mean? I'm going to be silly this time. I'm going to put my positive over here and my negative over here, just to switch things up. Will that bother you? Yes? Yes? Okay, I'll put the positive back, but you should be able to do it either way. Yeah? So that's what it should look like, basically. Is good? Okay, cool. Type 2. Because heating the ionic solid to high temperatures requires a great deal of energy, we often use an aqueous solution instead. But we can't do it for things like group 1 or group 2, which is why we still use type 1 cells for those. But we do have to then watch out for water, because water can be oxidized and water can be reduced. So in this case, our electrolyte, our salt, is aqueous, and our electrodes are still inert. If they are inert, what do you think we've made them of? Carbon, graphite, or we can use platinum here, right? Because now we're not worried about the platinum melting. Okay, so platinum or carbon. Gold, yes, but honestly, if I had to choose, platinum, just because that's the one that's most often referenced. Okay, so these two are best. Yes? Yep. You can just use carbon. Absolutely. I just bring these things up because you'll sometimes see do you know what I mean? Like if I don't give you the full picture, then you'll be like, platinum? Is platinum? Is that inert? You know? Yeah. Okay, so it's going to look like this, and you're going to have to figure out who gets oxidized and who gets reduced. All right. Consider the following electrolytic cell. Let's label our power source. It must say DC. And this time, just for funsies, we are going to put our positive on the right, and we're going to put our negative on the left, just so that you don't get too ingrained in, oh, it always has to be one way or the other. It's more common to put the positive on the left and the negative on the right, but either is really okay. So in this case, which direction would the electrons move?
Right to left.
They would move from right to left. So your electrons would go this way. Which would be the anode and which would be the cathode? Platinum would be, or sorry, not platinum, they're both platinum. The one on the left would be the cathode. And then the one on the right would be the anode. So which direction would the copper 2+ ions go? They would go to the left. And which direction would the sulfate ions go? They would go to the right. And if this were a multiple choice question, and it said, what substance is oxidized at the anode? I know that polyatomic ions don't really undergo oxidation. So I could just be like, oh, it must be water. Okay, but we'll go through the whole thing and show you why. Noisy people. Okay. Since electrons must move from the anode to the cathode, we cannot use alternating current, so we need to have a DC power supply. Okay, select the preferred reduction reactions. So for reduction, we actually have four possibilities. We have copper 2 plus, but we actually have copper 2 plus twice. Yes? And we have water. And we have sulfate. So out of these four, who is going to be the one that gets reduced? It's going to be the first copper because it has the highest E naught red, so it is the winner. Sulfate, even though if it was the highest, it wouldn't work unless you had hydrogen. Yeah, and so that's how you make your choice there. So that is our reductions. Now for our oxidations, oh yeah, and there's our reduction half reaction. Let's go to our next page. And again, we're going to put DC. We're making this our positive, negative, electrons go. I need to fix this. Fix. And what did we make these electrodes out of? Platinum. There we go. So for the preferred oxidation reaction, we need to read in the reverse direction because oxidations go in the reverse. So we are looking at these going this way. So sulfate can get reduced. Water can get reduced. Oxidized. Water can get oxidized. Can copper 2 plus get oxidized? No. So we don't even have to consider it because it cannot become copper 3 plus. Okay, and you won't find copper over on copper 2 plus on the right-hand side of the table. So out of these two, you have to remember you need to look at the oxidation potential and say which one is more preferential there. So that's going to be our water in this case. So sulfate will not, which just goes to prove that polyatomic ions do not get oxidized. Okay? And if you think about it, sulfate already has 4 oxygens stuck onto sulfur. How many more oxygens could you stick onto the sulfur, really? You know, it would be very difficult. Okay, let's write the overall reaction for this electrolytic cell and calculate the cell potential. So we have the oxidation half reaction. The reduction half reaction, again, was the copper one. So this is what we found on the previous page. Positive 0.34. And you do need to write this 10 to the negative 7 molar in there. Okay, if that's the reaction you're using, please do write that. And remember, you can use the reduction potential at the anode if you prefer. It would just be the opposite sign, okay? Red cat, there we are. And don't forget to use units in your work. Did you guys get negative 0.52? Yeah? Okay, good. I did my math right. Excellent. Okay, so there's our overall answer. What voltage is required? Whoa! Did I get the wrong voltage? This should be 0.82, not 86. Somebody said that earlier. I heard them. And I was like, I didn't know what was going on, so I was like, well, I don't know. Okay, so this should be, fix this. This should be negative 0.82 volts. Okay, that means this will be 0.82 volts, which means this will be 0.48 volts. Okay, sorry about that. What voltage is required to run the cell? Greater than? Positive 0.48 volts. Do you need to write this positive?
Yes.
Yes. What will be produced at the cathode? You got two choices. You got stuff up here or you got stuff down here. What would be produced at the cathode? Copper, okay, because that's our reduction reaction. Okay, so what's produced at the cathode? That's going to be copper metal, copper solid. What's produced at the anode? Oxygen gas, O2 gas, and hydrogen ions. Will the resulting solution be acidic or basic? It will be acidic because of that hydrogen that's being produced. Okay, and we've already labeled the cathode and the anode in our previous pictures. Show the direction of electron movement, show the direction of ion movement. We already did that, yes? So we don't need to go and do that again. Now we're going to look at a type 3 cell. Type 3 cell is just like a type 2 cell, except that the electrodes are not inert. And we specifically make them that way because maybe we need like the electrode to provide ions or something like that, okay? Oh, and this is wrong. Oh no. Yeah, what the bleep? This is wrong. Some metal. Whatever the next page is, 125. So we need to fix this here. Yeah, get rid of the platinum or the carbon because these are metal. Metal. Not both of them don't have to be active, but often they are. Okay? So, for example, a 1 molar solution of nickel fluoride is placed in a beaker. Also in the beaker are electrodes made of copper. An electrical current is passed through the solution and a reaction occurs. Determine the reactions at the anode and the cathode. What would be a good place to start for this question? Draw it out, okay? I'll go back to putting the positive on the right or on the left. So one thing you can do is you can simply list out all the things that are in the beaker that could possibly be oxidized. And then you can go through and you can cross out anything that couldn't be oxidized. You can just list everything that's there and then you can say, I know that blah, blah, blah cannot be oxidized. Do we have any that cannot be oxidized? I don't see nickel 2 plus anywhere on the right-hand side of the chart. So you guys can see nickel plus, 2 plus anywhere on the right-hand side of the chart? Nope, not on right-hand side of the chart. So we can just cross it out. What would I do with these other 3? I would look for their these are oxidations. So what would I want to look at? I would want to look and see what are their oxidation potentials. So E naught ox for copper, for fluoride, Now I've put down the values. I haven't put pluses or minuses yet. Do you guys agree with those values? Okay, should those be positive or should they be negative? They should be negative because they're all given on the chart as positive. Those are your reduction potentials, and so we need to make them oxidation potentials by making them all negative. Once you know those three values, what will you do? You're going to say, which one is the most favored? Which one is preferred? You look for the highest one. The highest E naught ox is preferred. And so that's going to be copper. Okay, so list them out. Cross out anything that can't get oxidized. Find the one that has get all their oxidation potentials and then choose the preferred one. Could you do the same thing for your possible reductions?
Yes.
Yes, go do it. And you'll notice I do all kinds of things. Like I write possible oxidations at anode just so I keep track in my head. I'm like, oh, the Cu is reacting at the anode. This time, which potential are we going to look at? Oxidation or reduction? Reduction, so we want the E naught red of these. Do you guys agree with me? Yes? Excellent. And so then what you can do is you can say over here, therefore, we would have copper being oxidized, Cu. The oxidation of copper goes to Cu, 2 plus 2 electrons. And for our cathode, we would have nickel 2 plus being reduced. And we were asked to find the two half reactions. So we have Cu at the anode and we have nickel at the cathode. So these are a bit of a pain in the butt, yeah, but they're doable, I hope. Yes.
For the table, you know how you wrote in brackets like at anode and at
Mm.
You're a little bit confused on that.
Okay. I just like to remember that that's just reminding me that my reductions are taking place at the cathode, so that when I'm giving my answer as to what reaction is happening at the cathode, I'm like, this one here is at the cathode. It's just keeping it in my head, because if I write it down, I am more likely to get it correct. Also, sometimes they'll be like, and you have an iron cathode and a copper anode. So you would need to be like, if you had an iron anode, then you would have to be like, oh, my anode doesn't have copper because it's not made of copper, right? So you would have to write whichever one you have wherever. Yeah. You don't have to write at cathode or at anode. You just need to be able to write it here. Yeah? For me, it's just a way of keeping track of things. But there's no particularly great reason for it.
But when we're writing like the chart out or the
Yeah. What do you mean?
Like I guess like the whole entire
Beaker. So if this were platinum, I could not include copper at the cathode, right? If this were platinum, I could not include copper in my consideration because there's no copper at the cathode, right? If this were platinum. Yeah?
I think that was that because like the ions move to like.
Oh yeah, they move to one side or the other. I mean, honestly, you're going to end up eliminating the ones that don't go there anyway, right? Because, I guess that's not, yeah. Because nickel does not go towards the anode, right? And fluoride doesn't go towards the cathode. You can eliminate them for that reason alone, right? Or you can eliminate them because they're not on the left-hand side. Or there's a lot of reasons you can eliminate things. Yeah. Just because sometimes it's easier just to list them, but you don't have to. Okay? Yeah. Now, there's this thing called the overpotential effect, which is not required for AP, but is required for regular chem. Yay! Something that we do in regular chem. And if you look on your chart, you are going to see the overpotential effect. Do you see that little dotted line and arrow? I am not going to explain to you how the overpotential effect works because I do not know how and why the overpotential effect works. I think at one point I had some sort of vague idea, but even when I did, I think it was pretty vague, right? And not like, I really understand this. It was mainly kind of like, maybe I kind of might maybe get it, but really no. What the overpotential effect is if you have a competition, and we're going to look at the reduction one first. This is for reduction. If you are comparing water with any of these ones in here, water loses.
What do you mean water?
So, water is normally 0.41, yes? But if you're comparing it with iron 2 plus, it becomes H2O becomes smaller than negative 0.76. If you're comparing it with iron, or if you're comparing it with Ag2S, or if you're comparing it with chromium, or if you're comparing it with zinc 2 plus. I don't want you to think too hard about this. I just want you to remember that whatever is within the bracket always wins compared to water. Wins in terms of this is the half reaction that will happen. You know how you pick the preferred reaction? You know how we were picking the preferred reaction? Like 2 seconds ago? What do you mean no? We were literally doing it just here. Who is the preferred reaction? The nickel is the preferred reaction. Yeah? You remember that? The one with the highest E naught red. Yes? Okay, the one with the highest E naught ox. Now, if we go here, it looks like water has a higher reduction potential than these 4 people here. But if they are present, water somehow gets dumped lower. Okay? So the moral of the story is that if you're like, who's the preferred reaction between water and chromium? Chromium is going to be the preferred reaction.
Why don't they just put water below?
Because the potential of water is negative 0.41 unless you're comparing it with one of those. Okay? So if you were trying to figure out the potential of water, like the cell voltage needed to make water get reduced, you would use negative 0.41.
And it's the same thing for
And it's going to be the same thing up here. So usually it comes into play. I would say that for these ones, you don't really have to worry about silver sulfide because who's going to use silver sulfide, right? That's kind of bizarre. It'll be for like either iron or chromium or zinc. Those guys will be preferentially reduced compared to water. Okay, even though they look like they shouldn't be. Up at the top, who do we really need to worry about? Probably chloride, bromide. Those are really the only 2 in there. Maybe mercury,
And is that one?
manganese 2+. This one is for oxidation. So this is the overpotential effect for oxidation. So if you're like, oh, I've got chloride in my beaker, it looks like my E naught ox is negative 1.36 volts, which it is. And I would look and I'd say, water, E naught ox is negative 0.82 volts. Water wins, except that it doesn't because chloride is within that little dashed line area. So chloride would be the preferred reaction compared with water.
I just remember.
Because those are the only ones that you're probably going to run across, maybe chromium. Everything else, I'd be like, I don't know. I mean, I suppose you could have. Usually the questions that you're going to come across, because this is, I would say probably those 2 are the ones that you mostly need to worry about. I mean, it could be any of them, but I think that bromide and chloride are the most common. Yeah? How do we feel about that?
Wait, but like, okay, so overall you're looking at like a higher.
Yes, overall you're looking at the higher one, unless it's in here, in which case all of these guys get preferentially oxidized over water. They win compared to water.
But wouldn't they already win either way?
No, because they're more negative. Because we're going backwards, right? Yeah.
Yeah. Okay.
So they win compared to water, even though they are more negative because we're looking at the oxidation potentials.
I didn't flip it.
Yeah, I know the whole flipping thing. It's flipping annoying, isn't it? Yeah. Okay, that was a bad joke. All right. So let's figure out what you guys are doing for homework. You have reviews to work on. You got to work on the reviews because your test is when? Thursday. Next Thursday. All right. And
I'm here to.
okay, I can't miss everything. There's a math test on Wednesday. There's a bio test on Friday.
Thursday.
I'm putting my test on Thursday. It's as good as it's going to get. It's not after the winter formal. So, All right. So homework is going to be page 127.
What, and then you said, you know.
Plus review.
Really? I don't remember that. Oh. No,
So I'm sorry, this is not going to be a nice weekend for you, I bet. Even if we're just chemistry, it would not be a nice weekend. But I know it's not just chemistry. It's chemistry and, yes,
It's always a lot.
I know.
One third, like, the day of.
Yeah. Where's Steve?